Hello, hello, hello. This is Nicholas. I have returned after a couple months of learning some math on my own. And I saw a friend yesterday, Lucas McCamey, and I was working at the ice cream shop, and he told me that he was doing math at dinner with his friend Jennifer. So I was just so happy that he was doing that. Now, Jennifer wasn't as much. But so this video is for Lucas because I wanted to kind of do some of my proofs for what the same concepts that he was doing. So in other words, he was working on a proof for the law of cosines and the law of sines, and he came up with two perfectly valid proofs. I just wanted to see, kind of give some explanation to my proofs. So yeah, that's this video. First, I would want to start with the law of cosines because I think that proof is kind of the coolest, to be honest. So let's do that one, yeah. So we're going to have the law of cosines. And what we're going to do is we're going to imagine a triangle, and we're going to imagine it in some coordinate system such that one of its vertices is centered at the origin. It doesn't matter which vertex, it doesn't matter which vertex, it doesn't matter which vertex, because without loss of generality, we could always just shift our coordinate system such that any other vertex we want would be at the origin. So now we're going to imagine all three sides of this triangle as position vectors instead. So that means we're going to have their tail at the origin, and they're going to be coming out like this. We'll call this vector A. We'll call this vector B. So now what is this vector right there? Well, it's what you need to add to B to get A. Right? So what do you need to add to B to get A? Well, you need to add A minus B, right? Because A minus B plus B is A. And so let's call this also vector C. So this red vector is the difference between A and B, and we're going to call that C. So what we're going to do now is we're going to dot C with itself. And whenever you dot a vector with itself, you get the magnitude of that same vector squared, because remember, in general, if you have vector u dotted with vector v, that's the magnitude of vector u times the magnitude of vector v times the cosine of the angle between the two. But if you have the same vector, the angle between the same vector and itself is 0, cosine of 0 is 1. So you get magnitude of c squared. Now, using the definition of c, c is vector a minus b dotted with vector a minus b. And that's the magnitude of vector c squared. Now, you may also remember that the dot product, it's a n-dimensional scalar operation. So in other words, it can be done in an arbitrary number of dimensions, and it outputs a scalar, right? It's sigma I equal 1 to n of u sub I v sub I. So in other words, you just multiply the corresponding components of the vectors together and then add them up. So what this definition of the dot product tells you is that it's distributive, right? And it's distributive just because normal scalar multiplication is distributive. So we kind of just transform vector problem into a scalar problem. And so you can verify for yourself that the dot product is distributive. I think that's a solid explanation, so I'm going to leave it at that. So I'm going to distribute this dot product, and I'm going to get vector A dotted with vector A minus vector A dotted with vector B minus vector A dotted with vector B plus vector B dotted with vector B, and that's still the magnitude of vector C squared. Now vector A, any vector dotted with itself, that's the magnitude of vector A squared. Then we have these two being the same, so minus 2 A dot B plus B dot B, which is the magnitude of vector B squared, is the magnitude of vector C squared. And then now, using the definition of the dot product here, this definition, we get the magnitude of vector A squared plus the magnitude of vector B squared minus 2 magnitude vector A, magnitude vector B, times the cosine of theta, the angle between the two vectors, is equal to the magnitude of vector c squared. And this is actually the vector form of the law of cosines. Of course, if you want to call this magnitude little a and this magnitude little b and that magnitude little c, then you'll get the familiar scalar law of cosines. In other words, just with scalars and not vectors, and you'd still get a squared plus b squared minus 2ab cosine theta is c squared. So that's a pretty complete proof right there of the law of cosines, and I've showed every possible step there. Normally you wouldn't show that much, but I want it to be totally unambiguous if you all are watching. The next one is the law of sines, and this one is even more straightforward, I think, but it has a cool little lemma that I would leave to you guys that would actually be a fun little geometric exercise to do. So again, let's start with a triangle, and I'm not going to use vectors for this. It's too straightforward. So we'll call this angle A, angle B, angle C. This is side A, side B, side C. And I always take the time here to remind people that the reason why we labeled the sides opposite of their angle like this is because it makes the most sense. So in other words, as the angle increases, the length of the side will increase, right? These two are in direct proportion to one another, and so it would make the most sense to label them in a way such that if this angle B is there, it's going to affect this side B right there, opposite to it. So those two are in relation to each other. It's not a random kind of by convention sort of thing. It's the most intuitive thing to do, right? If I were to make angle B 179 degrees, right, then side B would be very, very big, and side A and C would be very, very small. So that's just, I always, because most people don't know that, so I always take the time to kind of point that out. That has nothing to do with my law of sines proof. Now, here's the actual law of sines proof. So basic geometry, maybe trig, whatever you want to call it, proof, or not proof, but formula, is that the area, I shouldn't be using A because I used A for the angle. I'll write it out. The area of this triangle is 1/2 little a, little b times the sine of that other angle C. So in other words, the area of a triangle is just 1/2, and this formula really is just, see, if I were to draw this altitude right here, that's the height of the triangle H, but of course H is also just A sine C, right? Because if we have this here, then this part here is the sine, and that part there's the cosine. So what does that tell you? Well, this formula really is just 1/2 base times the height. So it just reduces to that form. And you can do a similar argument to show that the area is also 1/2 AC sine B, and it's also 1/2 BC sine A. And now you can probably already see where the law of cosines is coming up. If I take this whole thing and I multiply by 2 and I divide by ABC, and I can divide by ABC because the sides are greater than 0, otherwise we don't have a triangle, it would be degenerate. So 2 times the area over ABC is equal to sine C divided by C, because I divided this whole thing by ABC, and then the A and the B's would cancel, right? So I just have sine C over C. All right. So we get sine C over C, which is sine B over B, little b, which is sine A over A. QED, right? And so this is a more general version of the law of sines, actually, right? Because normally in the traditional law of sines, you'd only see this part right here. And in fact, this isn't even the full law of sines. Here's the fun little exercise I would leave to you all. Let's consider the circum circle of triangle ABC. So that's a bad circle, circum circle. Let me do that again. So it's the circle that circumscribes the triangle. In other words, it touches all three of these points. They're at the vertices. That's supposed to be touching there on the bottom left side. And those are the only 3 points where it touches. So we consider this circumcircle, and it's got its circumcenter, right? The center of the circumcircle, like right around here, right? And it has some radius, call it r. Then the full, totally general law of cosine says 2 times the area of the triangle divided by the product of all the lengths of the sides is equal to all this schmozkin, but it's also equal to r, the radius of the circumcircle of triangle ABC. And so this part here is the kind of fun little geometry exercise I would leave to you all. So, this isn't really a question, but exercise. So, prove that all of this stuff is also equal to r, the radius of the circumcircle. And I think that would be a good place to stop for this video. I'll probably be making a bunch more calculus and multivariable calculus videos kind of when school starts, because I've been doing a lot of that lately. I've been reading a lot of multivariable calculus, and hopefully we can do math this year, so then I could kind of record the calculus videos too and put them on here. Anyway, that's it. So